Okay, good morning. We've been talking about carbohydrates and very important biomolecules, as the last section of the text will give you an introduction really to what's to come if you're going into the biosciences. And chemistry-wise, you saw that the chemistry is reasonably limited, and we've already covered it, except that it's got the additional twist of being polyfunctional. So we have a polyhydroxycarbonyl type scenario. We have the possibility of making intramolecular hemiacetals, and we have basically then just redox chemistry and protection chemistry. So we can oxidize the alcohols, we can oxidize aldehydes, we can reduce the aldehydes, and then we can look at things like ether formation and ester formation. The polyfunctional nature comes in because we have an aldehyde and we have alcohols and we have a hemiacetal. And hemiacetals, as you know, we can turn over to acetals. So it's old chemistry as applied to a new system. So it serves as a review, it serves to reinforce what you've learned earlier, hopefully. And then we have the added twist of having intramolecular reactivity. The only other aspect that we've emphasized, and this is where Fisher projections came in, so we reviewed Fisher projections, was symmetry. And the symmetry relationships, when you symmetrize top and bottom, when you make both functional groups at the end of an aldose or ketose the same, you have to look for symmetry relationships with respect to the stereocenters. So there can be meso compounds which would be optically inactive, or just based on the symmetry of the molecule, C2 symmetry, rotational symmetry, which makes this thing still chiral, but it's got NMR type symmetry. So we can look for that. In nature, as I said, they are abundant. And one of the major features of sugars is their energy content and their ease of metabolism. And so they're the perfect fuels. Another aspect is recognition. All our cells are covered with particular sugar molecules. And because of hydrogen bonding, incoming species that would like to get into the cell, or the cell would like to pull in, will first have to pass the password, as it were, namely, will it be recognized by the first line of recognition, which is a sugar layer. Where this becomes, for example, very important is in blood types. Okay? We all have various blood types, A, B, and so forth, and that is primarily due to the fact that you have different sugar coding. Okay? And then energy storage, we started looking at how nature uses glucose to store and then use it in a variety of ways, not only just storage. One of the things that it does, it makes polymers, and it's interesting that glucose features very dominantly in all of these biopolymers based on sugars. And part of this, undoubtedly, is the fact that glucose has the stereochemistry that allows it in the cyclic pyranose form, in the hemiacetal form, to have everything equatorial. Okay? So this is a very stable arrangement. Notice that, as we noticed in terms of oxidizing the aldehyde function in aldoses, that, of course, sugars are intrinsically reactive. And even air, aldehydes are unstable to air slowly, and even air will oxidize aldehyde slowly to the corresponding carboxylic acids. So as a storage device, glucose itself is not useful, or any other sugar that has a reducing, can be oxidized, so it has a reducing function. So what nature does very cleverly, it blocks the hemiacetal function by making an acetal. We saw already a very good example of that with table sugar. Brilliantly, in table sugar, glucose and fructose block each other by making an ether link using the hemiacetal hydroxy of both of them. Okay? So they make an acetal that's an acetal to the sugar as well as an acetal to the fructose. And that stabilizes the molecule, and so it's perfectly air stable. As you all know, sugar can be, bought and kept for months and years, and it doesn't degrade. When in fact, if it were to be the free aldehyde, it would oxidize over a period of months or so, okay, and probably turn colored and so on. So here's another example. This is a polymer, and this is cellulose. We stopped here last week on this. And I briefly mentioned, although we rushed to this a little bit, so I'm going to do it again, that this is a polyglucose in which the hemiacetal function is blocked by making a bridge to the equatorial OH at C4 of another glucose molecule. Okay? So we have this equatorial OH of this molecule blocks the hemiacetal function, which is also equatorial. So it's a di-equatorial form of the linkage. And it uses the beta or equatorial OH of the hemiacetal. So this goes up to about 3,000 units molecular weight of the order of 500,000. You can imagine a long chain. And this is one way to store very efficiently, of course, a lot of energy. And then enzymes can start hydrolyzing here and liberating the individual glucose molecules, and then they are reactive and they get metabolized and do whatever they need to do. Another aspect of this, which we haven't talked that much about, but clearly, since these molecules are polyols, they all are capable of hydrogen bonding, and nature uses that to the hilt. In a polymer like this is basically a long line of structures that are decorated with potential hydrogen bonding units. And so it's used for structural materials. Okay. No longer on a leash. I can wander around. Okay. And so this is another brilliant concept of nature, using the OH bond, which, as you may remember, is only 5 kilocalories per mole, roughly, per bond. But if you start making a lot of them, then indeed you get something that's very strong. And if you make 1,000 of them as you go down the lines of such a polymer chain, then of course you have a 5,000 kilocalorie attraction between two strands. And if you do this, since the OH is on both sides of the strand, in a two-dimensional or even three-dimensional way, you get an extremely rigid construct. And this is one of the things that nature uses, to make rigid fibers and the like, plant materials and the like. So this is due to multiple hydrogen bonds. We'll see another brilliant application of this when we come to DNA, where DNA, the double helix, is held together by millions and millions of hydrogen bonds. So this is also an extremely stable arrangement. Part of the brilliance of this is that at any given bond, it's only 5 kilocalories per mole. So it's an extremely flexible, in that respect, structure with respect to one particular site. So enzymes and reagents can still go in and start nibbling away or do whatever they need to do locally, while the three-dimensional arrangement of these constructs stays untouched. Okay, so this is cellulose. So notice it's the beta acetal oxygen. It's pointing up in cellulose. Now we see the alternative. The alternative would be to go alpha, and nature uses that, and that's starch. Okay, so starch and cellulose are actually the same if you wish. They're diastereomers of each other. Okay? In one case, it's the beta linkage. In the other case, it's the alpha linkage down here at C1. So it's again binding to another molecule of glucose at C4. This dimer here is actually a disaccharide called maltose, which you may, it's in malt sugar, which you may have heard about. Anyway, if you make a polymer of this, you get starch. So this is a polyglucose with alpha-acetal links. And this is the fuel reserve that plants use. Okay? So the cellulose is primarily used for structural material, and this is for the fuel reserve. So this is the stuff that you'd like to stay away from if you're overweight, and so on. Okay? It's in potatoes, wheat, rice, and so forth. So this then hydrolyzes using enzymes again and to glucose. And an interesting experiment that some of you may have done accidentally to do is to take a piece of bread, which is starch, and keep it in your mouth for about a minute or a little longer. And as you do it, it will develop a very sweet taste. Okay? The reason that it's doing that is because the enzymes in your mouth start hydrolyzing at the acetal linkage, and you make glucose. And glucose, of course, has a sugar taste. So that's very, very sweet. So there are two major components of starch. One is amylose, which is the straight chain scenario. And then an alternative is amylopectin, which has branches. Okay? So the branching motif is also used. I'm not a sugar expert, so I'm not quite sure why this is, except that branching obviously imparts different structural capabilities. Branching also, in principle, allows you to access multiple sites, multiple equal sites of the same type of molecule. So you have more capability to attack. Look at the simple case butane. Butane has two methyl groups, so if you were to be an enzyme that just prefers methyl groups, butane has two of those sites. If you make the isomer, the branched form of butane, which is the tetrabutane, the tetrabutyl group with a hydrogen attached to it, it's got three methyl groups, so you have more access, if you wish. So that's amylopectin. And then the human fuel tank for immediate fuel access is called glycogen. But again, it's just the polymer of glucose. You don't have to remember this because those of you who are going into biology and biochemistry will have to remember this. But from a chemical standpoint, these are all just oligomers of glucose. Okay? There's more branching going on. The branches are longer in glycogen. And that apparently is essential for a now very quick production of as much glucose as possible. Because you have, because of the branching, many end groups, and the enzymes actually start attacking at the non-reducing terminals, at the end groups of these branches. And so obviously the more of those you have, the quicker you can liberate glucose, and that's what you want. So you want a quick injection, fuel injection device, basically. Glycogen. So when you're very exhausted after strenuous exercise, that's what's kicking in. And there's some brilliant mechanisms of these enzymes as they chew down the line. Okay, so you start chewing away one glucose at a time, and then when they reach branching points, they do all kinds of interesting acrobatics, which is part of biochemistry. This stuff is huge. Molecular weight goes up to 100 million. So that's a really enormous type structure. It's basically a big blob with multiple sites on which you can chew away to liberate glucose to give you energy. Now, another feature of sugars, which I briefly touched upon in nature, which I briefly touched upon in the introductory slide, is it imparts water solubility to assemblies, to structures, to molecules that are normally water insoluble. Since water is the solvent of life, in order to get reactivity, you got to get stuff into solution, and we've done this ad infinitum. It's exceptional that you can get two things to react with each other by just
grinding them up as a powder, although reactions like this are known. And so to get them into solution, to get something insoluble into solution, frequently what you do is you attach an auxiliary group that is similar in structure, similar to the solvent that you want to dissolve the stuff in, and then it will go in. And so nature uses that by just attaching sugars to something that is biologically important. So I've just picked a couple of examples. Here's a class of molecules that are used extensively now worldwide. It's one of the primary weapons against cancer. It's the anthracyclines. And the anthracyclines have this structure. This is the active part. It looks a little complex, but it really isn't. This is an anthracene frame, which is oxidized to the quinone frame. We've learned about quinones. And it's got next door a benzene diol or hydroquinone frame, and then attached to this is a cyclohexane that has various oxygen functions in a specific stereochemistry. These compounds were discovered in the, I guess, 60s by an Italian called Arcamone. And the anti-cancer potential was recognized very early on. And part of the anti-cancer potential is that this quinone function acts essentially as an alkylating group. Remember that quinones can react with nucleophiles, and you can attach things to them. So by a mechanism that I won't go into, it goes onto this position. It's the benzylic position that acts essentially as an alkylating group, so you can think of this as benzyl plus. And alkylating agents, in principle, are dangerous and can be carcinogenic or mutagenic because they can alkylate the bases of DNA. The bases of DNA have nitrogens that can be alkylated. You alkylate, and then in DNA replication, there is a mismatch, an error in the chain, and that leads to misreading and leads to a mutation, most of which, 99.9999999% of which or more lead to cell death. Nothing happens. But every now and then, one of these mutations can lead, evidently, to an event where the cell machinery starts going berserk. Anyway, so this is insoluble, and so in order to get it soluble into water, nature attaches the sugar. Okay, so this is basically just an auxiliary substituent. Notice that it is a modified sugar with respect to our normal sugars. It's got no oxygen here, no hydroxy, so it's a deoxy sugar. It's still a cyclic cyclic acetal in this case. Notice here's the anomeric carbon, or the acetal carbon, and it's attached as an acetal to this OH of the so-called A-glycon, which is the other part of the sugar. And it's got an amino group, so the OH has been replaced by amine. So adriamycin is one of these compounds, has an OH here. Daunomycin has an H here, and it's used particularly successfully in the treatment of solid tumors. And I've seen pictures of this in patients. It really is spectacular. You get an infusion of the stuff in quite, for medicines, large quantities, hundreds of milligrams at the time. And you can see as you take, a week later, 2 weeks later after treatment, you look at the tumor just shrinks away. So mechanistically, very simply, what happens here is the anthracycline intercalates, and here's a model of this, into DNA. We'll see more of DNA in the last few lectures. But it intercalates, and that also leads to eventually cell death. And so it screws around with cell replication. And by far the basis for most cancer treatments is that cancer cells replicate extremely rapidly compared to normal cells. And if you mess with the replication step, you stop the growth of cancer cells much successfully relative to the growth of normal cells, although most of these drugs also attack normal cells. So part of the principle is, it's sort of a catch-22 in a way, is to hit the cancer cells with poisons because the cancer cells are susceptible to these poisons because they're hyperactive and they multiply considerably. Okay. Another example, which is basically, if you just look at it on first glance, looks like a trisaccharide in which you have a furanose sugar attached at the beta, with the beta acetyl hydroxy to what looks like a semi-glucose molecule, except we have nitrogen here and here, nitrogen substitution, attached to another acetyl carbon of another molecule that looks like a normal sugar. But there's some interesting differences. Okay? This furanose here actually has an aldehyde sitting off here and a methyl here. Okay? Looks like there has been an intramolecular redox process because you really want to have an alcohol here and an alcohol here also. This guy, while on first sight looks like a sugar, is actually a cyclohexane. So nature, there's a mimicry going on here. This obviously is a much more stable assembly because it's actually all carbon six-membered ring. Still adopts the chair configuration, and nature for some reason thought that this was advantageous. And down here we have again a nitrogen hanging off here, and there's certain aspects of the stereochemistry are interesting. Perhaps very interesting is that this molecule uses an L-glucose rather than D-glucose. So the statement that all natural sugars are D is not quite right. Most of them are D. Every now and then nature picks the opposite enantiomer to impart whatever activity it wants. So this guy is called streptomycin, which you may have heard about. It's also a powerful antibiotic reagent. And this one binds to the ribosome, which is the ribosome is the enzyme, as so this blob indicated here, that's responsible for assembling amino acids to peptides. So it's a very important piece in cell replication. So again, misreading of genetic information leading to cell death. A lot of these interfere with this DNA replication business that we'll look at next week. Okay, so much for the sugars. Now let's move on to another class of compounds, or summarize what we've learned already about another class of compounds and expand a little bit on them, and that is heterocycles. So heterocycles are called such to distinguish them from carbocycles, which are rings based purely on carbon. Heterocycles are carbocycles in which one or several carbons have been replaced by a heteroatom. And for organic chemistry, by and large, the heteroatoms we're talking about are nitrogen, oxygen, sulfur, maybe phosphorus. And that forms by far the largest fraction of heterocyclic molecules. A really good one is shown here. You all know this one, and you've eaten that stuff, at least those of you who are coffee drinkers. Frequently, it's this section here, this is from the 5th edition, but how many of you can do without the morning cup of coffee? Okay, so this is the heterocycle caffeine that is responsible for the physiological activity of coffee. And you notice it's got one ring here with 2 nitrogens in it, another ring here with another 2 nitrogens in it, a bunch of double bonds, there's a carbonyl here, and just some methyl groups. Pretty simple molecule. It is somewhat reminiscent of a benzene ring, this ring, except that 2 of the carbons have been replaced by nitrogen, and it's a benzene ring that would have 2 carbonyl functions attached to it. And this one is a rather special ring. It's called a pyrrole, which has 2 double bonds here and here, and there's a nitrogen, which, as it turns out, has a lone electron pair that participates in cyclic delocalization. So we'll learn about that kind of aromaticity a little later on. So a normal 8-ounce serving has 135 milligrams of caffeine. I spent a sabbatical in the fall of 2004, about a year and a half ago, in Rome. So I learned to really appreciate Roman espresso. That has 100 milligrams of caffeine in less than an ounce of liquid. In fact, Roman coffee is famous for the fact that it's just a tiny amount. You basically just take the forerun of the high-pressure liquid chromatography extraction of coffee. And when you taste that, it is an incredible jolt to your system. So very few of you have had that kind of an espresso. But you can get it even at Roma's or any of the stores by watching them and tell them to take the cup away after about 5 seconds of water going out of the espresso machine. So you could try that as an experiment after lecture. Okay, I don't know whether you can see that. It's a little big. But there is a table. This one is updated. There's an older table in your book. It illustrates the point. By far, the largest proportion of all drugs, all medicines that we take have heterocycles in them. So the heterocyclic motif is extremely important for two reasons. One is recognition. The lone pairs of these heterocycles are very important to, in terms of basicity, lone pair basicity, to attach themselves to active sites and the like. And they're also important for activity with respect to reactivity, because the heteroatom makes the systems reactive. So as of 2003, so this is already outdated to some extent. This changes all the time. These are the top 10 US drugs. As of 2003, I think this is still actually number one, Lipitor. This is the ranking, 1 through 5 and 6 through 10. Lipitor or atorvastatin is a cholesterol reducer. Cholesterol-reducing agents have been the big craze in the last 10 years, huge money makers. I think Lipitor is now well over $8 billion drug. And notice it's got benzene rings attached. Here's an amide bond. Here's some hydroxys attached in a stereochemically defined manner, a carboxy group. And here's the heterocycle. Here's again this 5-membered ring, 2 double bonds and a nitrogen whose lone electron pair contributes to aromaticity. So this is an aromatic ring. Number 2 was Prilosec. That's an anti-ulcer agent. Here's a heterocycle. Notice that this looks very much like that, except that it's got now 2 nitrogens on it. And here's a ring that looks like benzene, except one of the carbons is nitrogen. This is called pyridine. We've seen pyridine before, actually, as a mild base. We've used it in order to mop up HCl in various substitution reactions and the like. It's also aromatic. Okay? And then there's an ether hanging off here, and there's a sulfonyl group, and so on. This one's called Zocor. You may have heard about this one. This is another cholesterol. It's another cholesterol reducer. And here's the heterocycle. This one is a lactone heterocycle. So it's a cyclohexane in which one of the carbons has become an oxygen. Notice that, rather, some of these, this one is very simple compared to that one in terms of stereochemistry. So synthetically, to make this is much more difficult than that. It's got 1, 2, 3, 4, 5 stereocenters, 6 stereocenters, 7 stereocenters. So that's a quite intricate molecule, and the stereocenters are all bulked up quite a bit. Norvasc is an antihypertensive, another 6-membered ring nitrogen cycle. This one looks like pyridine, except it's got 2 hydrogens attached to it, so it's a dihydropyridine. more like a cyclohexadiene in which one carbon is replaced by nitrogen. Here's again another anti-ulcer agent. Notice the motif. In fact, all of these compounds basically either treat cholesterol or ulcers or tension. And ulcers and tensions are related to each other. It's sort of a reflection of modern society, that these are the prime ailments that we are afflicted with. That's called Prevacid. This is Cyprexa, I guess. That's an what is that? Is that an antihypertensive? I can't read this. Celebrex, you all have heard about, is an anti-arthritis compound, very, very successful. Here's an exception. This drug here, which snuck up in 2003 as one of the big sellers, is actually a polypeptide, 165 amino acids, and that's an anti-anemic compound. This one is well known, Paxil, an antidepressant. Here's the heterocycle. Here's another heterocycle. And finally, Biox, that used to be a very successful anti-arthritic compound, and then it was withdrawn in 2004. And you hear about that a lot because there are all kinds of lawsuits because of the side effects, heart attack, things like that, that it's alleged to be associated with. So heterocycles are really, really important structures in medicinal chemistry. So let's look at some of the namings. It's actually quite simple. There are cyclic molecules that contain at least one heteroatom, so O, N, and S are prevalent, especially O and N. And so what you do is you just use the prefix oxa, aza, or thia, or phosphor in front of the cycloalkane. So it's an oxacyclopropane or an oxacyclohexane and so forth. To indicate this contains oxygen, aza for nitrogen, thia for sulfur, phosphor for phosphorus, titana if it's a titanium heterocycle, which we won't talk about. But it's the same principle. So here's oxacyclopropane. Common name is oxyrane or ethylene oxide. That's the three-membered ring oxygen compound. Here's a nitrogen compound. It's called an azacyclopropane. And when you have substituents on it, and on the nitrogen, it's an N-methyl azacyclopropane. So we're using the same N-alkyl nomenclature that we used for amines and then amides. Here's a thiacyclopropane. Substituents are labeled with the position that they're in, and the numbering always starts at the heteroatom. Okay, so the heteroatom is atom 1. So this is atom 1, this is atom 1, this one's 1, and so fluorine in this compound is at position 2. So this is 2-fluorothiacyclopropane, and if it had stereochemistry indicated, you would have to label it ROS. This is an oxacyclobutane, and this is an azacyclobutane. At 3 position, we've got ethyl, so it's 3-ethyl azacyclobutane. This is 2,2-dimethyl thiacyclobutane. This is an oxacyclopentane. Common name is tetrahydrofuran. The basic stem, without substituents, is used as a solvent, THF. We've used that ad infinitum as a solvent. It's basically a diethyl ether solvent in which you bend back the backbone and made a bond to make it cyclic. So it's a cyclic form of diethyl ether. And pulling back the ethyl groups from diethyl ether exposes the oxygen lone pairs more than usual, and so THF is actually an excellent ether solvent for that purpose, because if it's dissolving compounds by using the oxygen lone pairs. For example, in Grignard formation. Grignard reagents are MgX. The magnesium is electron deficient. So Grignards, as you may recall, can only be made in ether solvent because they pick up 4 electrons, 2 pairs from the ether solvent. So this at 3 and 4 has 2 bromines, and it's trans, so this is trans 3,4-dibromo-oxacyclopentane. And here's azacyclopentane. thiacyclopentane, and now for 6-membered rings, it's just cyclohexane. So this is 3-methyl oxocyclohexane. Common name is pyrane for this, or tetrahydropyrane. Remember, this is the stem we use for the name pyranose. Just like the 5-membered ring ether, the furan name was used for furanose. Azocyclohexane, common name piperidine, and so on. Now we come to the aromatic version of the heterocycles, and this is relatively new. Okay? So if you have a 5-membered ring and you put in from tetrahydrofuran and you put in the double bonds, you now have 2 conjugated double bonds, and there's an oxygen that has 2 lone electron pairs. And one of those pairs is used for cyclic conjugation, as we'll see later. So this becomes aromatic. It's a cyclic, delocalized, 6-electron frame. Same thing for this guy. This guy's called thiophene. So this one's called furan. So now we're really switching to common names because IUPAC nomenclature is a little lengthy. This one you would have to call an oxocyclopentadiene. This one a thiacyclopentadiene. So the common names are firmly entrenched. So this is thiophene. This guy is a benzene in which 1 carbon is replaced by nitrogen. So it's called pyridine. Notice that the lone pair in pyridine is perpendicular to the pi frame. So here, unlike these 2 systems, the lone pair is not involved. Nitrogen is just normally sp2 hybridized like carbon would be, and it donates 1 electron perpendicular to the frame of the molecule to make the 6-electron frame. It's completely identical to benzene. Benzene would have a carbon here and an electron pair in the plane. That electron pair, because carbon is to the left of nitrogen, would have to be, to keep carbon neutral, would have to be capped off by hydrogen. So it's a CH is replaced by N. Here's a benzo derivative that's called quinoline. So this is an aza analog of naphthalene. It's in fact 1-aza naphthalene. This guy is a benzo 5-membered ring compound. It's called indol and so forth. So there are a bunch of these compounds in which you have cyclic delocalization. We'll see some more of these a little later. In this chapter, we'll see more of these guys in the last chapter, because these kinds of structures are the basic frame of the DNA bases, or nucleic acid bases in general. So this one actually is added in. It is one of the bases. Okay, how do we make these? Brief review. We know how to do that. The best way is intramolecular SN2 reaction. So for ethers, for cyclic ethers, for oxocycloalkanes, this would be the intramolecular Williamson ether synthesis, chapter 9. This is the reaction on which we learned the rates, the rules for the rates for ring closure. 3-membered ring, fastest, 4-membered ring, slowest, 5, faster again, and 6, faster again. And the interplay between entropy and ring strain as you do this. So you just take an open chain compound that has a leaving group at some point, and you have the heteroatom that has a lone electron pair. Typically, it's used as the anion. Obviously, that makes it an even better nucleophile. And then you do an intramolecular displacement, and that makes the cycle. One special reaction we learned for oxocyclopropanes, remember this was the oxocyclopropanation, chapter 12, with peroxycarboxylic acids. Peroxycarboxylic acids basically transfer an oxygen to the double bond. They do so stereospecifically in a one concerted transition state starting with trans, you get trans, starting with cis, you get cis. What sort of reactions do they do? Well, we know about that already also. When the rings are strained, then you can do nucleophilic ring opening. When they're not strained, they're really quite unreactive. So either you you just don't, nothing happens to them, or you have to beat on them to make something happen. So 3 and 4 membered rings open up. So here is a case, 2-phenyl oxocyclopropane, you treat it with alkoxide or any nucleophilic type reagents, alkyl lithium, Grignard reagents, methyl sulfide, and so on. Ring opening will occur, and you get the OH backing off here. So this is one of those cases where the leaving group stays attached to the molecule, and the methoxias come in. So these are high-yield reactions. Here is an ASA. This one we haven't seen before, but the nitrogen 3-membered ring compounds are also reactive. The ring strain, remember, is on the order of 28 kilocalories per mole. So they're like loaded springs, and so ring opening will occur. So even nitrogen functions as a leaving group, although nitrogen is a much worse leaving group than oxygen. Remember, nitrogen is to the left from oxygen. Oxygen is much more electronegative, so oxygen pulls on this bond much more than this nitrogen does. But because of the ring strain, it's still reactive enough to cause this opening. And so now the nucleophile I'm using is an amine, and this works nice. Although notice, we do have to beat on it a little bit. This is much, much slower than this. This goes at room temperature. Fast. This you have to do 120 degrees, 16 days, but the yield is good. Oh, sorry, here's the yield. So this is 70% amine in water. And you get the ring opening. So this gives you a vicinal, as it's called, diamine. 4-membered ring compounds also open up. We haven't done much of that. And part of the reason for that is that to make the 4-membered ring compounds is much more difficult than the 3-membered rings. And that has to do with the fact that the intramolecular Williamson synthesis for making oxocyclobutanes is the slowest. So there are complications. Remember, it's an intramolecular SN2. If the SN2 slows down for whatever reason, this is now globally speaking, other things happen. Usually elimination. So you start seeing side reactions. Since you can't make these as easily as these, we've seen less of this chemistry. But the principle is the same. They actually do the same kind of reaction. And so with an amine, 150 degrees, bang, you open up. Yield's not that great. So these ring openings are usually done under basic conditions. But we've learned for oxocyclopropanes especially, acidic ring opening is possible. And so what happens here is that you are protonating first. That turns the oxygen into OH, which is a much better leaving group than O-. And now, under acidic conditions, it's the neutral nucleophile that attacks. Normally, the neutral nucleophile is not hot enough to attack if it's a nucleophilic oxygen to attack. But in the previous slide, we saw that a neutral amine is nucleophilic enough to ring open oxocyclopropanes, although you have to heat. So here under acidic conditions, you protonate. And remember that now, because of this protonated species, we have a full positive charge here. Charge control takes over as opposed to basic conditions. Under basic conditions, the SN2 follows the rules for SN2. The less substituted carbon is attacked for steric reasons. Here, it's the more substituted carbon that's attacked because it's got more positive charge. So this was an exception. Acidic type ring openings are generally used less. The simple reason being that whenever you have acid around, if there is a chance of doing carbocation chemistry, it will find it. And you know that carbocation chemistry is really basically a disaster unless the system is very well defined. So carbocation chemistry means SN1 and E1 rearrangements, polymerization, and the like. Okay, so for rings that are larger than 4, unstrained rings, relatively unstrained rings, these guys are really stable. So this is THF. THF is rock stable. That's why it's used as a solvent. And so you have to beat on this. And so synthetically, this is not used much. It's more interesting from a from a mechanistic point of view, if anything. So you have to treat this with boiling hydrobromic acid. HBr is a very, very strong acid. So this is strong enough to protonate here, and then when you heat, you do nucleophilic ring opening. So it first makes this, and under the conditions, this alcohol gets protonated again, and bromide displaces it, so you get the dibromide. But because of these rough conditions, you couldn't do this to a sugar ether, for example. It would just completely chew up the sugar, turn it into black goo. Okay, now what about the corresponding ring opening for the nitrogen analogs? You can't do that, just for the same reason that you can't convert an amine, an ordinary amine, the amino group in an amine, into an ammonium leaving group by just protonation. You can protonate it and makes the ammonium species, but that ammonium species just sits there. So ammonia as a leaving group is not as good as water as a leaving group. What you can do for alcohols, protonation, which turns OH into H2O, and then making it leave, what is feasible there is not possible for nitrogen. Why? Well, again, oxygen, much more of a polar. So it's intrinsically a much better leaving group. So if you take this guy and you argue, well, I'm going to ring open this with HBr, concentrated HBr, just like I ring opened the corresponding ether, it won't work. It'll just protonate and it'll make the salt and just sit there. But we know a way to turn, one way to turn the nitrogen into a leaving group, and that's by alkylation. And that's the so-called Hofmann degradation. Okay? So you can methylate it, which would be the equivalent operation to protonating, and permethylate. So you use excess methyl iodide that puts two methyls on here and makes the dimethyl ammonium salt. And it's that guy, in the presence of silver oxide, that then undergoes an elimination, an E2. Okay? So we don't use this for SN2 chemistry. We just use it for elimination. And that works. So two methyls here, base pulls off this proton, puts in a double bond here, the leaving group leaves. Here it is. It's left, and here's the double bond. And if you do it again, you put in another double bond in here. So this step methylates here, makes the ammonium salt, which makes it a reasonable leaving group, not as good as protonated oxygen, but reasonable enough that a strong base using silver oxide deprotonates here and does E2. Remember, silver oxide is nothing else but silver hydroxide, okay? AgOH. It's related to sodium hydroxide and sodium oxide. Na2O, when you add water to it, makes NaOH. So this is just a reagent that's used to generate Ag silver OH, hydroxide. And so it's hydroxide as a strong base, and silver is particularly useful here because it complexes to the nitrogen. So it helps to pull off the leaving group as well as to supply the base that eliminates it. That's a special feature of this Hofmann degradation. So other chemistry is the same as for the acyclic system. To remind you of a couple of these, for example, secondary amines. Remember, you can make the N-nitroso compounds by just using nitrous acid. So this is typically done by using sodium nitrite, NaNO2, in the presence of some HCl. That makes this, which is a source of NO+. And NO+ attacks the lone pair, and then you deprotonate and you make this. These N-nitrosamines, when they derive from secondary amines, are stable. Remember, when they're derived from primary amines, where you have a hydrogen sitting on here, it starts rearranging and eventually make N2 and the carbocation. And for tertiary amines, of course, you can make the N-nitrosonium salts, but it doesn't go anywhere. Okay. So in nitroso compounds, for these sulfides, we've seen that. That goes back to chapter 9. I don't know if you remember this, but sulfides can be oxidized to the sulfoxides and then all the way to the sulfones. Sulfur being in the third row here. There's valence shell expansion, one way to think about it. Or if you don't like that, you just write the dipolar resonance forms with plus on sulfur, minus on oxygen. That keeps you in the octet range. So that's just done with hydrogen peroxide. So sulfides are unstable in the presence of hydrogen peroxide, and they can be oxidized to the sulfoxides. And then we can methylate. That makes the sulfonium salts. Okay. So now what is new is this special feature of these cyclically delocalized aza or heterocyclopentadienes. We'll do that after the break. So perhaps the best way to look at these compounds is to compare them to cyclopentadienyl anion. That was one of the compounds where we noticed that you can expand the 4n+2 rule to incorporate charge systems if they have odd number of carbon atoms. So remember, this guy was derived from cyclopentadiene, which had 2 double bonds here and 2 hydrogens here. And we noticed cyclopentadiene, the pKa was on the order of 15.5, extraordinarily low. It has a pKa that's the same as methanol. Okay? So methoxide will pull off that proton, for example. And tertiary butoxide will pull it off such that the equilibrium is a 1,000-fold to the right. Why? Because when you pull off an electron proton from here, you leave an electron pair here, and that starts to enter into conjugation with the other 2 double bonds. So it's the 2 electrons on 1 carbon that starts delocalizing. And you can write resonance structures that put these 2 electrons here, 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 and here. So on average, there is an excess electron density distributed over all 5 carbons. So you have 6 electrons distributed over 5 carbons. 1.2 electrons, as it were, per carbon. And that imparts stability to this thing because it's a cyclically delocalized 6-electron frame. So the picture that we used for CP anion, cyclopentadienyl anion, was this. Completely symmetrical structure as shown by X-ray, and indeed it's the charge is distributed evenly. So that all carbon bonds are the same, all CHs are the same. In the NMR spectrum, it's a nice singlet, okay? As opposed to cyclopentadiene, which is sort of a reasonable mess because it's got 3 different types of hydrogens and they're all coupled to each other. Okay? So when you replace one of these carbons with a heteroatom as in the next compound, which is called pyrrole, now we don't need a hydrogen that's, you replace CH2 with NH. Okay. And so now we have a nitrogen here. And I should put in the hydrogen again. Sorry. Here you go. Now think of this as a nitrogen atom, okay? And there are 2 electrons in here, just like in the cyclopentadienyl anion, but they are part of the nitrogen lone pair. And so now we are neutral because nitrogen is trivalent. And it's this electron pair that starts delocalizing with these guys. Now, and that imparts aromaticity. But because nitrogen is a different atom from carbon, of course, the system is not completely symmetrical anymore. Okay, so there's slight asymmetry in it. But nevertheless, it tries to symmetrize structurally so that it's trying to make all the bonds the same. So this is a shorter bond than you would have expected for a normal amine carbon. And these bonds are slightly longer for a full double bond. And this bond is slightly shorter again. So you're trying to delocalize the bonds, and you're trying to avoid bond alternation. You can't completely avoid it because nitrogen is a completely different atom from carbon. The electronegativities are different and so forth. And the symmetry of the system, of course, has also been lifted. But nevertheless, this compound called pyrrole has unusual stability associated with it because of the cyclic delocalization. You can see this sort of in the electrostatic potential maps. Here, the red area of the delocalized system is distributed nicely, evenly over the 5-carbon system. And here, it's sort of also distributed. Here, down here is the nitrogen, so the H is down here, perpendicular to this frame. It's also fairly evenly distributed over the 5-atom system here. Same thing holds for furan and thiophene. In the case of furan and thiophene, because we are further to the right even than pyrrole, we don't even need a hydrogen here. So now we have 2 lone pairs. But notice the oxygen and sulfur, which we typically always thought as sort of semi-sp3 hybridized, if they're hybridized at all, now it prefers sp2 hybridization because that puts one electron pair, one lone electron pair, smack into a p-like orbital that is perfectly aligned to delocalize. And the other electron pair is just sitting there in a sp2-like orbital sticking out in space. So this is, again, a manifestation of the powerful driving force of aromaticity that imparts special stability to these molecules. And so by all criteria, the heat of formation data, structural data, and as we'll see in a minute, also NMR data, which is perhaps the most useful for a practicing organic chemist, we have a ring current in all of these, which de-shield the alkenyl hydrogens. They move them to the left, just like as in benzene. There's another feature that imparts special reactivity of these, particularly in electrophilic aromatic substitutions. And that is that's sort of related to the extreme example of this, namely the cyclopentadienyl anion. If you have 6 electrons distributed over 5 carbons, as opposed to benzene, 6 electrons over 6, per carbon you have much more electron density on each carbon. And the same thing is true here. If this electron pair really kicks into the delocalized pi frame, then we are adding electron density to the delocalized pi frame. And so all these guys are relatively electron rich relative to benzene. So they all undergo electrophilic aromatic substitution faster than benzene does, even though we are talking, particularly in these 2 cases, about atoms that are more electronegative than carbon, so that inductively they're actually slightly withdrawing, but because a full electron pair is given into the system to cause the cyclic delocalization, the pi frame is electron rich. So electrophilic aromatic substitution is good. Okay, just looking at these orbitals of what I just did with the model, but pointing out the nitrogen more clearly, you can see here's the 5-atom frame as opposed to cyclopentadienyl anion, which would have a carbon here. We have now nitrogen with a lone electron pair sitting here, and there's an NH bond, and this electron pair is donated into this frame. If you look at furan and thiophene, now we have one to the right in the periodic table. Oxygen and sulfur is divalent in these cases. So we have 2 lone electron pairs. Notice that X hybridizes to sp2, and so this is a p orbital that's delocalized with these 4 electrons. And then there's another electron pair and an sp2 hybrid. So the hybridization changes somewhat around these atoms to facilitate cyclic delocalization. You can do this also by doing resonance structures. In the case of benzene, it was pretty simple because we had two equivalent resonance forms, the cyclohexatriene and the two possible arrangements. Here it's a little bit more intricate because you're starting out with a neutral, but one of the atoms, the nitrogen in this case, donates a full electron pair in the next resonance form as you move electrons around. That makes it positively charged, and conversely, the receiving carbon end becomes negatively charged. So you get dipolar structures. So starting from here, for example, to go all around the ring, that puts a plus here, the double bonds here, and a negative charge here. You can move this electron pair in here and this electron pair out. That gives you this dipolar structure, which is equivalent to that, obviously. Left versus right carbon bears the negative charge. And then you can do it again. It puts the negative charge here, and then again puts it here. So you can have the negative charge all around the ring on each carbon when the positive charge is on nitrogen. So again, this indicates that donating this electron pair into the system in principle puts negative charge on all of the carbon atoms. And that makes these carbon atoms relatively electron rich relative to benzene. So this shows up in NMR also. In NMR, because of the intrinsic asymmetry, of course, we have three types of hydrogens. There's the NH hydrogen, and that, remember, NH, like OH, and to some extent SH, is pretty variable. It depends on how wet your solvent is, what the temperature is on hydrogen bonding, and the like. In this case, it's broad, so it's broadened typically, and so it's broad here too, and it shows up at around 8. But the other two are very nicely resolved. Okay, so this hydrogen and this hydrogen, they're coupled to each other, so you see some splitting, and one is at lower field than the other. And the one that's at slightly higher field, they're both close, and they're both deshielded, by the way, so they're relative to a normal alkenyl hydrogen, which would be more on the regime over here. And the alpha hydrogen, or the hydrogen at position 2, is more deshielded than the beta, and that has to do with the dominance of the resonance form in which the nitrogen pair kicks in and puts in a negative charge here, the enamine type resonance form. So we can view this, ignoring now the cyclic delocalization, in a more localized picture as an enamine, amine group attached to a double bond. And remember, enamines, we use them as masked enolates. That is, we use the fact that these were neutral compounds in which the electron pair donates such that the beta carbon becomes electron rich, and we use that for alkylation. So in normal enamines, you can alkylate at this position. That gives you an imine cation, which we then hydrolyze to the carbonyl. And that allowed us to alkylate alpha to a carbonyl, avoiding the problems of enolate basicity. So if you just focus on this resonance form, that puts a delta minus here. That shields this hydrogen slightly relative to this one. Okay, so we got two effects here, by the way, that are fighting each other with respect to chemical shifts. One is the relative electron richness of these two carbons. Making a carbon electron rich means that the hydrogen attached to that carbon has a vicinity that's relatively electron rich. Remember, relative electron richness means shielding. So if you make something very electron rich, it moves to the right. If you make it electron poor, it moves to the left. Electron withdrawing groups move a signal to the left. So the electron richness moves these guys to the right. The aromaticity moves them to the left. So overall, aromaticity clearly wins. And these guys, or to put it differently, these guys, based on the ring current effect, would be even further to the left, where benzene is. But they're slightly not quite as far to the left due to the aromaticity because of the electron richness, which goes the opposite way. So clearly they're aromatic. That's the bottom line, based on the NMR criteria. So the same thing shows up in carbon. Now, carbon is not as diagnostic of ring currents because the chemical shift window in carbon is way larger, and the ring current effect is only 1 to 2.5 ppm. Moreover, the ring current, as it were, flows over the carbons, so it's not really, sometimes not clear to define in which the carbons lie in the shielding or deshielding zone of the ring current, the local magnetic field. In fact, the first approximation, they're right in the neutral zone. So ring currents are not diagnostic for C13. Okay? So that's in a way okay, because then you can focus more on charge effects. So again, the charge effect shields these guys somewhat, and the beta carbon is shielded more than the alpha carbon. And they show up in the range a little higher field than a normal alkenyl carbon, but not very largely. Normal alkenyls are between 120 and 140. Okay? So they're in that regime. And the beta is more shielded than the alpha. Mass spec. We now know how to do mass spec. So this guy shows a nice parent ion. The parent ion is odd, and that's the unusual feature of nitrogen because it's trivalent. So you get an odd molecular ion. It's exactly at 67, and indeed it's the base peak. It's 100% peak. Then there's fragmentation. When you blast this with 1,200 or whatever, 1,600 kilocalories per mole, it does fall apart. You can see that it seems to like to break this bond here. To kick out cyanide, this is cyanide or CN, and this is HCN, and this is protonated HCN, looks like. Okay, so this thing seems to break here, and then it starts falling apart by making cyanide. The CN triple bond is a very stable unit, so it likes to fall apart in this manner. IR. IR is pretty uneventful, except that, of course, in pyrrole we have an NH bond, so the NH bond shows up around 3,400, and there it is. Very strong band. The rest of it is basically fingerprint. So how do we make these things? There is a general way of making all of these guys, and that is by a condensation reaction that involves a 1,4 dicarbonyl compound. Okay. So these two carbonyl functions in a 1,4 relationship. And it's called the Pal-Knorr synthesis for pyrroles, and people have then extended it, so variations of the Pal-Knorr synthesis work for all of them. Okay? And basically what you do is you take this dicarbonyl function, treat it either with an amine that makes the pyrroles, or phosphorus pentoxide, which is basically just a dehydrating agent. Phosphorus pentoxide eventually leads to phosphoric acid. It's the anhydride of phosphoric acid. It's very hygroscopic. It reacts quite violently with water. So it wants to pick up water, and it rips out 2 water molecules from this, and that makes furan. And you'll see in a minute how it does that. P2S5 is just the sulfur analog of phosphorus pentoxide. It's the anhydride of thiophosphoric acid. Also hygroscopic, wants to be hydrated. It rips out water where it can. So it's these 3 reagents that do this. So let me give you an example. If you treat this dicarbonyl compound with P2O5, out comes dimethyl furan. How does that go? So I'm spelling it out for you here in step by step. First of all, carbonyls can always be in equilibrium with the enols. Indeed, under these conditions, phosphorus pentoxide is the anhydride of phosphoric acid. There's always a little bit of acid around, period. So the acid catalyzes, and I'm doing 2 steps in one go, the enol formation. So you protonate on the carbonyl, deprotonate here. That makes the enol. Remember, that equilibrium is fast. It's basically a tautomerization from the keto form to the enol form. Equilibrium is on the left, but you make it a little bit of this, and that's crucial. Now, this can be protonated again, off and on, and that activates this carbon with respect to nucleophilic attack. So that protonation makes this susceptible to attack by this OH. Notice that this is nothing else but hemiacetal formation. Carbonyl is attacked by alcohol. It just happens to be the alcohol of an enol. Okay. So the enol attacks here. That makes the hemiacetal still protonated. That's the first species that's formed. Then you lose proton. That would make the hemiacetal period. Then you reprotonate here. So I'm writing these without writing the intermediate neutral species. So essentially, this proton jumps from here to here. But it does so by coming off and then back on. That turns this OH into a good leaving group. Okay, so the leaving group leaves. That makes this guy. And then you lose a proton to make the double bond. This step, normally, in the presence of an alcohol, would make the acetal. But in this case, you're deprotonating because the driving force is to make the aromatic furan. Overall, what are we doing here? We're losing 2 molecules of water in this step to turn this guy into this guy. Sorry, 1 molecule of water. You're losing 1 molecule of water. Take it back, here it is. To dehydrate basically this dione to make the corresponding tetrahydrofuran. So topologically, it's a dehydration which is affected by the dehydrating agent phosphoric acid. All right, so here's an example. P2O5, 150 degrees, 62%. You get this fused furan. Here's another example. This dione here. Now with P2S5, same reaction. You heat it up, it dehydrates it, but in this case, you have sulfur. Sulfur replaces the oxygen in this step, and you get the corresponding thiophane. So this is the same reaction that we just did with P2O5, which put oxygen here. With P2S5, it put sulfur here. How does that go? Well, it goes through converting the carbonyls into the thiocarbonyls. So P2S5 exchanges carbonyl for thiocarbonyl. It does that in a sort of simplified manner. Here's P2S5 in an abbreviated form, similar to P2O5, so you can replace all these by oxygen. That's the same thing. Notice that if you hydrate this, you get the thio analog of H3PO4, namely H3PS4, thiophosphoric acid. The exchange occurs basically because this is very electrophilic. Okay, so a lot of delta plus on this because of the polarization of the PS bonds. So it attacks here, and I've written it sort of in an intramolecular manner. Attacking here makes this plus, so this makes this electrophilic. So actually a sulfur from another molecule of this comes in and attacks with sulfur here, and then you just, by the reverse, kick out oxygen. So it's easy to exchange oxygen for sulfur by the sulfur attacking here and then the oxygen leaving later. That turns the ketone into the thioketone. Then this behaves just like a ketone and makes the enol. So this is the ene-thiol, and the ene-thiol then reacts by making the thiohemiacetal analog of the hemiacetal. So the mechanism is the same. Crucial piece is that oxygen is exchanged for sulfur. Finally, do the same thing with an amine. For example, this, again, dione with the amine makes the corresponding pyrrole. If you have ammonia, it would make the parent pyrrole with primary amines. You get the alkylated pyrrole. And this also goes through a similar form, a similar mechanism as the other guys. Now we have nitrogen. Nitrogen comes in and first makes the enamine, just like the carbonyls make the enol and the thiocarbonyls make the ene-thio. And it's the enamine that then attacks, makes the nitrogen analog of the hemiaminal, and then you keep on going. The driving force in all cases is aromaticity of the ring. So it's one reaction applicable to all three heterocyclic systems. We'll talk some more about this on Thursday. Thank you.